Right, so I'm just going to go through this fairly quickly for discussing all 5 questions. Just look at the first one, and here you need to realize that cos cube x is actually cos x to the power of 3, and to perform this in the differentiations, we really are using this formula to do this. Okay, now next. It's very simplest product rules and explains often in class that this is really 2 functions, and once you realize that, that would becomes quite straightforward. Okay, the next questions. So these questions, the key part to prove this is actually somewhere right here, and just use the double angle identity. As you can see here, cos 2a equals to 2 cos square a, subtract 1. So what we have done is just treat the 3 data as a, and you do this. And do the same for sine 3 data, right? And using sine 2a equals to 2 sine a cosine a. So that identity will help you to work with sine 3 data and eventually get you to the cotangent. And this final equation of tangent is pretty straightforward. Just sub the pi over 6 into the dy dx, which will become your m, the gradient, the x and y, and use that to use this form to find the equation of tangent, and that's it. So to the next questions. So right here we are asked to state the equation of L. So if you don't show any working, but how this is done is fine. A good sketch will be very useful, and then you write this up. So 90 minus 135 is really the from the position vectors of OP, and also this will be the the components of OQ, and from that you just get this. Okay, and by using this also, because here this drawing, I hope is clear to you, that to find n, what we're going to do, we find NQ and then use the dot product of NQ and OQ, and because it's perpendicular, it's going to be 0. Discover the value of T, and then you get your N value using those XYZ here that actually in the parametric form will be as above. It's here, as above here. And finally, so once you have the coordinates of n, it's fairly easy to show Qn is really 3. So the part of question 4 is very textbook question, so it's really you should know by now how to do this. So he says that the P2 is parallel to P1. Now that means all the coefficients of x, y, z are the same except for the right hand side, the constant. So when you sub this value, 837, that means the coordinates, and then to find the constant, and it should be 25. And to find the perpendicular distance, uses distance to of a point to a plane formula, and the drawing is something like this because D is on the plane P2, so you can find this D to P1. That is also the distance between the 2 planes, and the value should be this one. And on the inductive argument questions, I do expect that you're able to do the first couple of parts because they are not really on the inductive argument yet. It's really trigonometric functions or on and differentiations. So I'm spending this one by using, of course, cosine A plus B, the compound angle, and and you get this, and you're able to see that k is 1 over root 2. And then moving on to the next one, here you just need to differentiate, and you keep things simple. You always do that, and then show this, just derive these functions and get whatever you want. Of course, you use a product rule because ex and cos functions are the 2 different functions, and then you get this and this, and So and yeah, and simplify this. So here you can see this is a common thread that in the later part where you keep using the something like a formula in A, and this is because from the A, whatever you could say about this is that you can now say that cosine theta minus sine theta is equivalent to could be replaced by root 2 of cos theta plus pi over 4. So this is basically what we did here. It's a cos some angle minus sine some angle, some argument, and then so we could write root 2 at cos that argument plus pi over 4, and that's what we'll be doing the next section, I mean the next purple section. And you will be able to show this is the case 2ex. And so when you look at the next one, so key here again, you can look at the work later, but the key here is this A is being used again to perform this, and then the next part we derive the d squared y dx squared to do this on the third degree, and again we use A again. So because there's a common common approach that you could keep doing this, that's why we can then argue that because the statement is true for 1, 2, 3, and by inductive argument that we're going to use this A formula again and again, the statement then is true for all n greater or equal to 1, and because we could prove the fourth degree and the fourth order and the fifth order and so on. So, and that's it.